Hello dear students of plus 2 medical and non-medical respected teachers. Today I am going to discuss two applications of Biot Savart'S law. Because I have discussed Biot Savart'S law in previous video. So you can check Biot Savart'S law in that video, which contains magnetic effects of current. So what are the main applications of Biot Savart'S law? So first of all, we will find the magnetic field at the center of a circular coil carrying current. Suppose we have a circular coil carrying current I in the clockwise direction, say, as shown in the figure, having center O, radius R. Let an element AB of the coil carry current of length dl. Let I is the current flowing through the coil and it has n turns. Then, by Biot Savart'S law, magnetic field due to the small current element of length dl carrying current I at center O, that is at a distance r, is given by dB is equal to mu naught I upon 4 pi dl sin theta over r square. This is Biot Savart'S law. Now, in this case, angle between dl and r is 90 degree. So, sin 90 is equal to 1. Therefore, dB is equal to mu naught I by 4 pi r square dl. Or B is equal to mu naught I upon 4 pi r square integral dl. Because magnetic field due to each element and will be acting at point O and it will be added. Therefore, B is equal to mu naught I by 4 pi r square into 2 pi r. So, r cancels, 1 pi cancels, 2 cancels, 4, it comes 2. So, we get B is equal to mu naught I by 2r, which is the required expression for magnetic field due to a coil carrying current having one turn. If it has n turns, then B will be equal to n mu naught I by 2r. So, magnetic field due to each turn will be added. So, direction of this magnetic field is given by right-handed thumb rule. So, curl your fingers of right hand in the direction of current and put thumb at the center. So, magnetic field will be directed inward the board, or to be directed normal to the plane of the coil, directed inward. So, if current direction is reversed, magnetic field will be outward. So, we can find direction of magnetic field due to a coil carrying current at a point on center by using right hand thumb rule. Then, second application is we have to find magnetic field due to a coil carrying current at a point on its axis. So, suppose this is a coil having n turns and radius r. The coil is such that half of its plane lies below the board and half lies above the board. So, it is like this. So, OX will be the axis of the coil. Let P be any point where magnetic field due to this coil carrying current I is to be determined. Let an element of length dl at A join A to P. Similarly, let an element of length dl at A dash diametrically opposite. So, join A dash P. Then, magnetic field due to each element at P will be normal to this AP and A dash P dash in this direction. By using again right hand thumb rule. So, coil is coming out. So, dl cross r, it will be like this. So, dB, length is same, current is same, so magnitude will be same, direction will be different. So, let this angle is theta. Then this angle also will be theta from geometry. Let x equal distance of point P from O. So, r is the radius, then AP will be equal to under root r square plus x square. Then this magnetic field dB can be resolved into two triangular components, dB cos theta along y axis, dB sin theta along x axis. Similarly, this dB cos theta along py dash and dB sin theta along x axis. So, each element will produce magnetic field at P which can be resolved into two rectangular components, dB cos theta and dB sin theta. Now dB cos theta, dB cos theta are equal and opposite. They will cancel each other's effect. So it means magnetic field along y-axis will cancel each other in pairs, but dB sin theta will be added. So magnetic field due to each element at P will be dB sin theta log Px. So therefore total magnetic field will be integral dB sin theta. So then magnetic field P at P due to each element is dB sin theta. This we have proved. So by Biot Savart'S law, dB is given by mu naught I by 4 pi, I dl, angle is 90 degree. Angle between dl and this vector, vector AP is 90 degree. So that dl sin 90 degree. This 90 of theta is different. So dB is equal to mu naught I by 4 pi, dl sin 90 upon AP square. AP square is distance of the element from the point. So it will be mu naught I by 4 pi, dl upon r square plus x square. Square root the whole square means r square plus x square. This is equation number 2. Now, therefore, total magnetic field due to the whole wire carrying current I at P is given by integral dB, or mu naught I upon 4 pi r square plus x square can be taken outside the integration because r is constant, x is constant. So it will be integral dl sin theta. So sine of theta from this right angle triangle, that will be r upon under root r square plus x square. So substitute the value of sine theta. That can also be taken outside integration because r and x is constant. So integral dl. So integral dl will be 2 pi r again, circumference. So b is equal to mu naught I r upon 4 pi r square plus x square 3 by 2. 1 plus 1 by 3 by 2, 2 pi r. So 2 cancels 4. So pi cancels. So we get b is equal to, if there are n terms, it will be added. So b is equal to n mu naught I by 2 r square upon r square plus x square power 3 by 2. Equation number 3. This is magnetic field due to a coil carrying current at any point on its axis, and coil has n turns, and direction of magnetic field is given by again by right hand thumb rule. So magnetic field will be along OX, along PX, directed outward. If direction of current is reversed, magnetic field will be towards left. So we can find direction of magnetic field at a point on axis of the coil. So special cases. Now at center, x is 0. Suppose P lies at center. Special case. X 0. Suppose x equal to 0 here. So it will be r square r3 by 2. That is r cube. ऊपर r square है, r square cancels with r square, so we have n mu naught by 2r only. The same expression, magnetic field at the center. So B is equal to n mu naught by 2r. This is general expression for magnetic field, and if point lies at center, so it will be n times mu naught by 2r. When x is greater than r, when point is far away and very large as compared to radius of the coil, then r square can be neglected. So neglecting r square in this question, so you have x square 3 by 2, it will be x cube. So n mu naught by 2 pi 2 I r square upon x cube multiplied by pi and divided by pi to give it new shape. So n mu naught pi r square is area. So n mu naught I a upon 2 pi x cube. N I a is called magnetic moment. M is equal to N I a, current into area of cross section. So it will be mu naught m upon 2 pi x cube. So or B is equal to mu naught m upon 2 pi x cube. So which is required expression for magnetic field when radius of coil is very small and point is far away from the center of the coil. And when x is greater than r, when x is equal to r, when radius of the coil and this distance OP is equal to are equal, OP is equal to r is equal to OA, radius of the coil. Then put x is equal to r, so r square plus r square equal to 2r square. So it will be 2 3 by 2 power r cube. So simplifying it, so n by 2 mu naught I 2 raised to 3 by 2 into r. So it will be n mu naught I by 2 raised to 5 by 2 over r. So when point lies at finite distance, which is equal to radius of the coil, then magnetic field is given by this n mu naught I by 2 raised to 5 by 2 over r. So which is the required expression for magnetic field due to coil carrying current at a point on the x-axis. So it means magnetic field due to coil carrying current is maximum at the center and decreases as we move away from the center on either side. So becomes zero at infinity. So this is all about magnetic field due to